Good morning, good evening, good afternoon to everyone around the world. Welcome to the last workshop for advanced track this quarter. We made it this far, so it's awesome. So as usual, we have the feedback form, which contains all the links you'll need. We'll drop that in the chat right now. The attendance code is Luge, if anyone's interested in that as well. And we can get started. So first off, we want to talk about projects again. So we have with us Edmund, who's on the projects team here. Edmund?
Hello, you wonderful people. I am here, your friendly neighborhood incoming projects officer for next quarter, and I am here to talk a bit about our projects for next quarter as well. And so you may have heard a bit about it already, where we've been doing this awesome project about Kosovo leaves this past quarter, and everyone was able to do this wonderful project with real world impact, where you're able to take tens of thousands of images of Kosovo leaves, which is a very vital food source for lots of different countries around the world, and use image processing to determine what diseases are there. And next quarter, we're excited to expand our project choice into something that is also within the realm of image processing, but also something that is a bit different. And the problem scope is that instead of having a bunch of different images with a bunch of different types or with a few amount of disease types, now we're doing it the other way around, where you have very few images for lots of different types, lots of different names for a specific whale. And so this may sound extremely intimidating. However, I'm here to emphasize that you absolutely, like, the fact that you are here sticking through week 8 is really amazing. And that is all you need to be able to apply. So if you have any interest whatsoever and you are willing to make a commitment, then just hit that application link and fill out that form. Even if you are not 100% sure that you want to go see this through, that is perfectly fine. You are completely welcome to fill in the application form, because we will be sending an RSVP afterwards for people to confirm for sure if they want to be part of projects. And if you have any questions whatsoever, you are perfectly free to drop a question in the Discord or feel free to message me. And again, I just want to stress the fact that you are here is enough qualifications that we need. And this also applies to anyone who is not attending live and is just watching on YouTube. So thanks for listening to me, and I hope to see you next quarter.
Awesome. Yeah, thanks a lot, Edmund. And yeah, like you said, please apply to projects. It's an amazing opportunity. Really take all you've learned here and apply it. Awesome. So today we're going to be continuing with the guided project that we started last time. So last time our objective was to build a CNN to classify images in the SAFAR 10 dataset. And we started off with this skeleton notebook. It just had some very basic structure. And throughout the workshop last time, we ended up looking through PyTorch documentation, really trying to figure out how we can implement this model. And at the end of the last workshop, we finished defining our CNN. So we had the pieces in place, and now our next step is going to actually to come up with all the training and testing routines. And then, of course, the most important part, keep improving our models. So to quickly recap, SAFAR 10 was this pretty large data set with 60,000 images, 10 different classes, stuff like trucks and horses, and it's completely available through the Torch Visions library. Oops, I clicked on that mistake. Okay, so the original skeleton notebook is right here, but we know a lot of you couldn't show up last time. So if you don't have, so if you haven't already filled out your notebook partially, we've implemented the first bit of it for you, and we can start off from this point in today's workshop. And of course, right after this presentation, we're gonna briefly go over what we covered last time as well. So like we did before, the PyTorch documentation is kind of the most important part of this workshop. Learning how to look through this documentation, how to search for different functions, different APIs is a really essential skill. And it's kind of pretty much all you need to do while implementing a model. Like no one ever memorizes what all these functions mean. You have to look it up every single time. I keep clicking on these links, I'm so sorry. Great. And logistics-wise, we're also going to create a separate breakout room just for questions. So if anyone has any specific doubts they don't want to share with everyone else, or if you want to share your screen and have one of us help you debug, just message us and we can hop into the breakout room with you as well. But of course, we encourage you throughout the session to keep asking questions in the chat. This is meant to be very interactive, and we're not going to provide as much information as before. So again, so structure-wise, we're going to start off with this partially filled notebook. We're going to first go over what we did last time. And the way this workshop is structured is we're going to show you a blank cell and say, this is what you need to implement. Then you're going to go to PyTorch, figure out how you want to implement this. And we're going to put like a rough estimate of how much time it should take you to implement this. Again, this is very rough. So each cell will contain a little number which says how long you should take to implement it. After some time, we're going to just simply give you the answer because obviously this is not a test. You don't want to hold you back. So we're going to keep making progress really slowly. But the most important thing is that you guys implement this yourself. So the links here should contain the partially filled notebook or the original skeleton notebook. We have the CNN and PyTorch workshops that we covered. A lot of it is very useful. The PyTorch workshop that we covered has a very, very similar format. So you can find a lot of good stuff from this workshop to put into this project. And of course, please ask us questions. Last time we had a really nice interactive session where everyone just kept asking questions, and that was awesome. So we hope to keep that up today as well. Awesome. So are there any questions? Okay. If everyone is good, then I'm going to hand it over to Jenson to share the notebook we came up with last time.
Can you guys see my screen or notebook?
Yep.
All right. So this is the partially filled notebook that I have from last time. So let me start the runtime real quick here. Okay, cool. So last week we downloaded our data sets from Torch Vision. And we also created our train and test loaders. And last but not least, I think we completed the implementation of our CNN class down here. So let's actually now create an instance of our CNN class. Takes a while to run. Okay, so if everything is implemented correctly, you should see like something like this. So if you don't see something like this, please let us know. We can definitely help out with that. And okay, actually, let me pause here for some questions about the CNN class in case anyone, I guess, maybe like didn't show up last time. So all we did in the constructor here is just define all the layers that we need. So we have a convolutional layer here, we have a pooling layer here, we have another convolutional layer, and then we have a flattening layer, and then some fully connected layers at the end. And then in the forward function, we basically just compose these functions together, these layers together in a way that allows us to do forward propagation throughout CNN. So yeah, if there's any questions regarding to the CNN class, please let us know.
I just have a quick question. I wasn't able to make it last time, but so what are like when you're doing your in channels and out channels, how did you decide on those numbers, or are they like arbitrary and like just trying to find it for it?
That's a good question. So the in channel of your first convolutional layer has to be 3 because that's the number of color channels we have in our input images.
Mm-hmm.
And then the out channel here is actually a hyperparameter, so it's a design choice. So this is basically like this corresponds to the number of filters that we're using for this convolutional layers. So in this case, we're using 6 filters, so that's why the out channels here is equal to 6. And
okay, got it.
Basically, like since the out channel here is 6, then the in channel for our next convolutional layer has to be 6 as well. And then the 16 here is also like a design choice. So yeah, hopefully that answers your question.
Okay, was there any intuition behind why you chose 6 and 16? Or like,
I guess not in particular, but I guess for the first convolutional layer, like the number of features that we're trying to learn is like less, because I think it's some like lower level features. Whereas in the second convolutional layers, we want to learn, there are like more ways to aggregate the higher level features or the feature map of the first convolutional layer. So that's why we have 16 here.
Yeah.
I mean, you can definitely tweak around these numbers to like see like different performance results.
Yeah, a very common design choice when designing CNNs is that you start off with a small number of filters, and as you go on, it becomes longer and longer. So the volume that you get outputted, the feature map, becomes like longer and yet thinner, if you see what I mean. So you initially start something like, like really like a very few channels, but it's a very large image, and then it becomes kind of smaller but much longer, but towards the end. That's kind of a common design choice.
that makes sense. Thank you so much.
Yep, no problem. All right, so if everyone is good on the implementation of our CNN class, let's move on to our next part. So the next part is just choosing the right loss function. Hopefully this shouldn't be too difficult.
Yeah, so make sure to look at the previous workshop, the PyTorch workshop, as well as the PyTorch docs. This answer should be literally just one expression. So, oh, and logistically again, so this workshop kind of depends on y'all's progress, right? We're not gonna go forward unless everyone's done. So if you give us some kind of reaction, some kind of message in the chat when you're done, that would be really helpful as well. Since it's so few of us, it's much better that we're all on the same page.
I guess I'll give it like 3 more minutes. Or if everyone is done, then I guess I can go through it now, but I guess I'll be monitoring the reactions.
Okay, so kind of a pre-question, right? There's a kind of a hint mentioned here that we're doing classification. So before you at least implement it, what do you all think the loss function should be? It's only once you figure that out, can you go and like figure out how to actually write up the code for it. So what do you all think the loss function should be? Okay, we have an answer which is sort of correct. So the loss function that we're going to choose will include softmax. But what is the loss function? Softmax is kind of the okay. So everyone seems to have got it. So it's in fact the cross entropy loss. And now what you all need to do is figure out how does PyTorch implement cross entropy. So literally just find out what that API is.
All right, so I guess the way you would figure out what the right loss function would be just, I guess, look up on Google's. So I believe it's under torch.nn, and then you can look up cross entropy loss. And yeah, here's the documentation. So yeah, this is the class. So actually in this case, I believe all the default values for parameters should work. So just be nn dot cross entropy loss. All right, so the next cell is where we define our optimizers. So there are actually like a multitude of options to choose from, but that being said, like not all optimizers are created equal. So some optimizers will definitely work like better than others in most scenarios. But yeah, feel free to experiment with different optimizers. I'll give you guys like maybe like 5 minutes to figure out which one you would pick. So
Yeah.
someone asked, would Atom be good here? The answer is yes. Atom, like if you're not sure like which optimizer to pick, Atom is usually a good choice. But yeah, now that I show you how to look up okay, sorry, I got a call just now. Okay, so now that I've showed you how to look up PyTorch documentations, feel free to do the same thing for the optimizers. Also, if you're done, then feel free to let us know. We don't want to like wait for too long if everyone's done. Okay, one person is done.
Yeah, how is everyone feeling about looking at the documentation? Like, is everyone comfortable with that, or do you need any more help? Like, let us know what you're thinking right now. Because what I'd suggest is simply Googling two words, So yeah, so we say someone's saying it's really massive, it's sometimes hard to find things. That's absolutely true. What I'd say is Google is your friend. So it's Google plus the PyTorch docs. Always Google something like PyTorch and the word you're looking for. So like PyTorch, Adam, you'll get it. I think Google has a much better search engine than PyTorch right now.
Yeah.
So that should be all you need.
So as you can see, like once I type torch.optim, I get like torch.optim.atom.
Mm-hmm.
And then here's actually like the documentation for an entire class. So what I can do here is I can actually explicitly search for Atom. So as you can see, like it puts me in the right place. So yeah. So basically, yeah, I think I'm just gonna use Atom for this, but feel free to look at other optimizers as well. There are definitely like a lot of interesting choices. So the way
What else? Sorry, go ahead, Jensen.
Oh, okay. I was just gonna implement the cell. But
Oh,
if you have anything to add,
yeah.
then yeah.
Yeah, I was actually going to suggest, right? When you look at the documentation, I know it can look like really, really scary with all these hyperparameters. What I'd suggest looking at is the little examples that they have. The examples usually show the hyperparameters that you most often tune. So right now, we never covered Adam in depth in advanced track, and most people use it the standard default Adam that the creators made. So what I'd suggest is in this situation, just don't bother messing with too many hyperparameters. You have a bunch of examples. So Jensen, if you could scroll up a little bit, let's see. I mean, literally all of them have some example or the other, right? And they usually show the hyperparameters that you tune most often, like let's say learning rate or what parameters to optimize over. I'd say just look at those key parameters and don't try and not get overwhelmed with all the massive list of parameters that they accept, because you could tune it to like anything you want technically. And if you see here, the example that's on the screen, that's kind of a standard thing. You just show what parameters you need, what learning rate you need. And that's pretty much all we ever really mess with. So let's wait a quick minute to make sure everyone found those docs and could write something up. And we can implement it after that. And yeah, thumbs up would be awesome as well if you're done. So we have a question. Why do we normally pick such a small learning rate? So okay, that's a good question. It's certainly a design choice. Again, learning rate is like you can make an entire industry on picking which learning rate to use. But the reason we usually pick a small one is because the weights of the model are really small. When we initialize a model randomly, we initialize it usually with a value between 0 and 1. As a result, the weight values are really small. So you don't want to like take gigantic steps while updating it. Does that make sense? Awesome. Okay.
Does everyone has a chance to make an attempt to define our optimizer here? If so, I'm just gonna go ahead and I guess implement it. So yeah, so the Adam optimizer is under torch.optim. And then the first parameters are the parameters of our models. So just model.parameters. And then I believe the second parameter here is actually the learning rate, but I'm just gonna use the default value. And I guess for the rest, I'm also gonna use the default values. But feel free to change the hyperparameters as you wish. All right, so the next part is it's definitely where the fun begins. So this is where you implement your train function. So this is a little bit more involved, but we did something like similar in, I believe, the PyTorch workshop. So yeah, feel free to refer to that. I guess another place with more information would actually be the torch.optim doc. I think this code snippet here is pretty helpful. So yeah, I guess I'll give you guys like maybe like 10 to 15 minutes.
Yeah. And if you feel really, really stuck, like say something. You don't want to, wait 15 minutes and then everyone's stuck still. As you make progress, let us know. Oh, I'm done with this one. This one worked out well. This one's really difficult to implement. Just let us know what you're thinking as well. Maybe a good starting point. We put a little question here. What is the first thing to do before starting training? I think that's something we should all answer and keep as a mantra while doing PyTorch. What is the first line of code that we should always have? Look at the PyTorch docs as well to get a look at this as well. Actually, take a look at the PyTorch workshop. That's why I think I stressed it a lot when I was talking last time. Okay, that's very good. Very good. Does everyone remember that? So we have Halen who said that we should do my model.train. So yeah, that's right. So we set the model to be in training mode. And that's super important. Maybe not necessarily for this particular implementation, but very, very important in general.
Yeah, this is actually very important. So this is actually
Yeah.
where a lot of bugs can arise if you forget to do model.train or model.test or eval, I guess.
Yeah.
So yeah, basically if you're like going over your test data set and you forgot to set a model to evaluation mode, then you'll end up like training your model on the test data as well. So that's definitely not something we want to do. Can you explain the comma syntax? You mean for batch inputs, comma, batch labels, and train loader? Okay, so basically each item in the train loader is like a tuple. So the first number in the tuple is basically our batch inputs, which is basically just all the pixels in our, I guess, image. And then the batch label is just a number that corresponds to each of these classes. So there are 10 classes, so there are 10 different labels, I believe from 0 to 9. Yeah. So this is just something you can do in Python.
Should we have a outer for loop for like the amount of epochs?
Oh, that's something
No,
we'll do
so
later. So that's
yeah,
actually, yeah, so that's something we would do like down here. But yeah.
The function says run it for one epoch. So the function's definition is train one epoch. So just make this function and we can keep calling it in our outer loop.
Oh, okay, I didn't see that. Cool.
So based on the PyTorch workshop, at least, or any other doc, what is one of the pieces that you should have in that for loop? Like just at a high level, what pieces do you think you should have? Okay, that's one of the pieces for sure. Yeah, so we have a couple of people who are saying reshaping, and that's very true, right? So what you reshape to should depend on how you define your model. So I'd suggest taking a look at that, how you define your train data versus how you define your model, and the two should be really compatible with each other. So yeah, try and reshape your data.
All right, since someone said zeroing out the gradient, so I'm just gonna implement that line. I'm actually gonna do it at the beginning, but you can also like do it at the end of your loop.
All right, did everyone manage to figure out how to reshape their input? Not yet. Okay, let's go to a minute more. Yeah, so it depends again on how you've defined your inputs. So the way we define our inputs in this template of a notebook, we wouldn't even need a reshape, I think. But it really depends on how you defined your test data set or training data set. And that's not something, it's a case by case basis on how you defined it.
So,
Sorry, go ahead.
So in this case, would it be like changing the dimensions of the picture?
So yeah, so again, it kind of, it depends on how you've defined it again. So PyTorch requires it to be in a particular way. It requires a particular order of dimensions. It requires, batch size first, then channels, then X, then Y. So I don't know how you all have defined your train and test flows. The way we've defined it, it's exactly that order. But if you haven't defined it that way, you're going to need to permute those dimensions. But okay, maybe Jenson, you want to scroll up to how we defined our loader?
So this is the thing, I guess the test model that I defined last time. So I guess last time I created like a random tensor with 16 as the first dimension. So that's the batch size. And the second dimension here is 3, which is the number of channels. And then the last two dimensions here is just the number of pixels on each, I guess, axis. So as you can see, like the output before the fully connected layer is 16 by 1024. So this is definitely what we would expect if we did the math. So yeah, that's what the batch input would look like. So in this case, we don't actually have to reshape. But yeah. If you did something different, then you might actually need to reshape.
So if you've just copied this notebook right now, you know how to reshape, go on to the next step I suggest. But if not, it is actually very, very important. And PyTorch will be very like, it gets really annoyed if you haven't, you don't have the right input shape. So I'd say double check, take out one of your samples, make sure it's in this like format. So batch, channels, XY. And if it is, then awesome. Otherwise, make sure you reshape. But I think we can assume that everyone has a similar thing, hopefully. If not, please feel free to let us know. So what other steps do you think we should move on to? What's the next step? Yeah, absolutely. So we have a suggestion that we make our predictions. And that's a great suggestion. We should absolutely do that. So does anyone sort of figure out how you might make those predictions? It should be very intuitive how we call our model using our inputs. And in fact, I'd suggest maybe put it in the chat itself. What line of code do you plan to put?
Run it through a model. Yep. Exactly.
Yep. Very good. So all we do, our model is just one big function, all said and done. We just call it with our inputs.
Yeah, so in this train one epoch function, we kind of just treat our model as a black box. So, yeah.
Great. Does this make sense to everyone, what we're doing? If not, please let us know. And if so, I guess we can go to the next step. What do you guys think the next step should be? Okay, we have another question. Compute the loss. Okay, that's great. That's great.
Yep.
How might we do that?
So remember, we define things like criterion and optimizer and our model. So look at the parameters that we're passing into this function. Hopefully that should be intuitive. Use the loss function.
So people are saying, yeah, so how do we want to use the loss function? What arguments should that loss function take? What does it depend on?
Criterion predictions, labels. Yeah, actually that's exactly correct.
Okay, sure. Yep. Good stuff. So while Jenson starts that, let's pause for a second. Does this make sense to everyone? Again, we don't want to rush and leave anyone behind. Does this make sense?
Yeah, also if we're going too slow, feel free to let us know.
Yeah, but the point is definitely for you all to implement this yourself.
All right, so the criterion is just the function parameters. So later on, we're going to pass our criterion here into this function. But for now, we're just going to assume that we have our criterion.
Yeah, criterion is just, yeah, it's a variable name, exactly. And yeah, criterion is just another fancy name.
Yeah, it's one of those fancy names. So what should we do next after we have computed our loss? I guess that would be a good way to think about it. Backprop. Yep, exactly.
Yeah.
So
and
our loss here is
so
actually just
figure out how to do this.
So the loss here is actually just a tensor, so we can do something like loss.backwards. So backwards is the function that you can call on a tensor to, I guess, backpropagate the gradients. And now we have one more line. So I'll let you guys figure out what this final line should be.
Yeah, and try and figure it out yourself by looking through the documentation. Like find out what the exact line of code should be. That's pretty important. I guess while you're looking, I have a question for all of you. So we just computed loss.backward, right? But we didn't store that value anywhere. Is that correct? Was that wrong? Is that what we're supposed to do? Where did the gradients go? So does anyone have an answer for where the gradients are? And this is important. It's important to understand what's going on under the hood. Okay. So we have a couple of answers. In the tensor, maybe. Doesn't the tensor have an attach underscore grad or something? Yeah, so that's vaguely right. So the tensor, in fact, has a field which stores the gradient. And does anyone want to guess what that field is? It's actually quite nice to sometimes just inspect what the value is. Sometimes it's all zero, and you're like, okay, that's not good. So, or sometimes it's all nan, and that's not good either. So, I'd suggest, since we're giving you these pieces of code, for an arbitrary tensor, what is the field that stores that gradient? And it's a good exercise to figure all this stuff out. So for a tensor x, I'd say x dot question mark. Okay. So does everyone remember? So okay. So in this black box implementation, we've just said that our tensors are these things which can store gradients. You remember back when we did the PyTorch workshop, how we actually specified that the tensor should keep gradients. What was the parameter that we told the tensor to say that, hey, listen, you must store gradients? And that's important parameter as well. And we have an answer for the previous question, which was loss.grad, which is absolutely right. We just say x.grad stores the gradient. So it is slightly maybe non-intuitive that the tensor itself is going to store its gradient. Backward doesn't kind of throw out the gradient tensor. It is stored within that tensor itself. And yeah, I think this is an important understanding question. How do you specify that the tensor must store a gradient? What is the hyperparameter called? And this is something we covered in the PyTorch workshop as well, so you can feel free to look back at that. But make sure you know what that parameter is and why it's there.
Okay, I'm actually gonna do a demo here, so.
Okay, so in the tensor, does that mean in the loss variable?
Yes. So the loss is
Yeah,
also
so
a tensor.
loss is a tensor, yeah.
Gotcha.
Yeah. So in our case, since we're doing everything through PyTorch's nice API, it automatically makes a tensor which requires gradients. But if you define something manually,
Whoops.
it requires
There's
I
a
think.
bug. Hold on. Oh, it's not requires grad. Is it requires grad? Or is it require? Okay, I think I just typed this wrong somehow.
Okay, so it's one of the two, I suppose. But yeah, so when you're defining your tensor manually, you must specify that it requires grad, because otherwise it's just not going to track the gradient. So it'll just say, oh, field undefined or something like that. Right now it's fine, but there are times in life that when you want to implement your own model from scratch, which is actually something you do a lot in real life, that you want to specify this parameter. Oh, I think it's requires grad. Let me, yeah, requires underscore grad. You've shut tensor.
Oh, okay. Oops, I think these have to be floating points. Okay.
Oh,
Totally forgot. Because you can't complete the, wait, what?
Huh.
That's strange.
Oh, Jensen, I think it's a small t. Might be a small t tensor.
Is it?
I think it might be.
Oh, lol.
Yeah. Lol. Okay.
Lol.
Nice.
Okay, let's compute some. Let's do some operations. I guess just square them, and then I guess I'll just add them up. So we can inspect x.grad, and then we get a tensor back that stores the gradient.
Mhm. Maybe just as an exercise, Jensen, just remove the requires underscore grad parameter and let's see what happens.
Uh,
Let's make sure that PyTorch is
might throw
being
an
sane
error.
as a yeah, it should. Yeah,
Yeah,
absolutely.
so you can't do
you
backwards.
great. So as you guys see, it's very important to specify requires underscore grad, and PyTorch will complain if that doesn't happen. Okay, I think we can get back to our model.
Yeah, also make
after this
sure
digression.
your the values in your tensors are floating points, because you can't like take the gradient if the values here are discrete. So that's very important as well. Okay, so hopefully everyone has figured out what this last line should be. So it's basically we're just making a step in our gradient descent, or whatever optimizer that we picked. So it's just optimizer.step. And yeah, that should be our testing done, or training done. And now we can move on to our test function here. So again, like, what's the first thing to do before testing? Feel free to answer in chat. Model.eval, yep. That's correct. And yeah, I guess I'll give you guys about like 10 minutes to implement our test function.
Yeah, this should be very similar to the training function, the first bit of it. But the second bit, you might have to look at the previous workshop, the PyTorch workshop to implement that. So we've also included some other helper code just to visualize what's happening. But we want you all to focus on the actual body of the loop.
So I think the test function is actually a little bit shorter than the train one epoch. I think there are actually only 2 lines that you have to write.
Yeah, but obviously, feel free to split it up as well. Don't have to do everything in one line of code. Remember what the operations are once you have your. Okay, actually, we can make our predictions if you want. That's not even a problem.
Yeah, I think we can make our predictions like right away.
Yeah. We have a question. Can we avoid reshaping if we're working off the partially filled example? The answer is yes. If you're working off exactly what we gave you, then you probably don't have to reshape.
Yeah, I guess if you call if you create a train loader and test loader like this, you don't have to reshape.
Where does the test?
Okay, so
yeah, go ahead, Jen.
Someone asked, where does the test function or testing data access the weights and bias from the model? So the answer is from this parameter here called model. So basically what we're doing is we're passing our CNN into the test function. So that's how we are able to access our the model and its parameters. I guess another thing is our model is actually global, so we can also access it that way, but
Probably not a good
think,
idea
I
to
think
keep it
passing
global.
it as a parameter is definitely better programming practice than using like global parameters all the time.
Yeah, so how do we get the first line? How do we make our predictions? This should be very, very straightforward. What do you all think?
So that should be very similar to how we get our batch outputs, but with a slight twist. So like we did before, we're just gonna pass in our batch inputs into our model. And then there's something else that you have to do here. I'm trying to see if you guys can figure it out.
Yeah. As a test of understanding, what so make sure everyone's on the same page, right? What is this model of batch inputs spit out? What kind of a object does it spit out? I mean, it's a tensor, of course. What kind of a shape does it have? And this is again very important for your understanding to make sure that you figure out what the model is actually spitting out. Does my question make sense to everyone? What is model of input spit out? Like what is the output size of our entire model?
So as you can see from a summary, the number of out features
Okay.
here is 10.
Yeah. So you have an
yeah.
answer, right? So 10 numbers representing the probability of each class, which is exactly right. And that's perfect. So once we do that, we like Jacob said, we need to figure out which one is the largest in that output. So that's what we have done here. We've done an argmax. So which index corresponds to the highest probability? So yeah, we said, wait, does this line of code make sense to everyone? What we've done in this predictions line of code? This is a good time to ask any questions about that.
Okay, I guess everyone's good. So correct here is just for, I guess, computing the test accuracy. So a prediction is correct if it is equal to the label for that sample. So hopefully that should give you enough hints to be able to implement this line. I guess if someone has an answer, feel free to type it in chat. It's definitely more interesting if you guys are able to come up with the answers.
Yeah, and efficient programming in NumPy is really nice. So if you use NumPy functions, use broadcasting, all that stuff, it's very good. It's much faster, and it helps a lot to develop that kind of thinking. Yeah, that's awesome. So we have a really good answer. Just you want to type it out in the chat in the notebook itself.
Oh yeah. So someone suggested predictions double equal sign. I think it's the batch labels.
So you missed out the S on prediction.
Oh, lol. Thanks for pointing it out. So this basically gives us like how many predictions are correct in this batch. And then so what we want to do here is we want to sum it up. And so, yeah, after we sum it up, this whole thing should be a tensor. So in order to get the, I guess, like a value, we have to call dot item on this tensor. So yeah, that is exactly correct.
So okay, we have a couple of questions, right? Isn't batch labels a string? And the answer is no. So batch labels will be a set of numbers from 0 to 9. So we don't ever work with like strings. So you see plane, car, bird, cat, deer, dog, frog, horse, ship, truck. Those correspond to 0, 1, 2, 3, 4, all the way up to 9. So that's how it is within the model, and we've written it here for our own purposes, just so we have an idea.
Yeah,
Does that make sense? It's always a number. Sorry.
So batch labels is actually a tensor with I guess the dimension would be the batch size. So that's why we're able to equate these two values. And the reason why we're summing is because like so predictions double equal batch labels would give us another tensor that would be like 0, like whose values would be 0 or 1. So if the predictions is equal to the label for a particular sample, the value will be a 1 for that index. If it's not, then it'll be 0. So in order to get the total number of I guess correct predictions in that batch, we have to compute a sum. Okay, let me run this cell. So the last part here is just implementing the entire training and testing routine here. So to do that, we can implement a for loop. So this hopefully shouldn't be too complicated. Let's see if we have more questions.
Yeah, the first question is len of test dataset. Which line of code is that? Oh, I see over there. So what we're doing is simply dividing by the number of the number of images in our batch. In the number of images in our.
So I guess the intuitive explanation here is like this correct here starts from 0, and then for each batch we're adding the total number of correct samples in that batch, and then at the end we'll just get the total number of correct predictions in our entire test data set. So to compute the accuracy, we have to divide by the number of samples we have in the test data set.
So in one epoch, do we run through every single image in the test data set?
Yes.
Yes.
That is correct.
Yeah, so to be more specific about the question, right? So if the print statement is inside the for loop, then we divide by the batch size. Since it's outside, we divide by the entire test data set. And we have another question: does item return only one value? And that's correct. So dot item, the function, is meant to take a tensor, which is like like 1 by 1 by 1 by 1, some weird 100-dimensional tensor or whatever, which contains actually only one value, and kind of pop out that one value and say that this is just a number.
So if you call like item on like I guess a tensor that has more than one value, it'll actually give you a value error. So yeah, that was just to illustrate like when can you use item and when can you not use item.
So is everyone good with the testing loop? Does that make sense to everyone? Any other lingering questions?
I guess I'll just do like 10 epochs here. But if you guys want to do like more epochs, feel free to do so. And yeah, I guess I'll just let you guys, I'll give you guys like a few minutes to figure out what the correct code should be.
So yeah, please use the functions that we just defined and just call them with the model, your loss function, everything else. It should be a few lines of code.
Yeah, so this whole loop should only contain like 2 lines. Actually, I'm gonna add a print statement at the beginning. So I'm gonna print out what epoch this is. Just so we can compare like how our model is doing in different epochs. Feel free to type out your answer in chat if you're done. Let's see, train 1 epoch model, train loader, optimizer, criterion device, test model, test loader device. Okay, that's exactly correct. So, oops. So like we said, we should call the functions that we defined earlier. And then we can just pass in like, I guess all the parameters. They happen to have the same name. But, just test. Okay, it's just test.
So okay, so someone got an error saying that the batch labels and the predictions have a different size. So that seems a little more specific to debug. I'd suggest maybe printing out what the size is just before you call the function and try and debug it. It's almost definitely specific to your situation, so I don't know what that would be.
Yeah, so everything is implemented correctly. You should see something like this, where you have like the epoch number, and then the end of epoch loss, the end of epoch accuracy, and I guess your guess and label for like, I guess 4 images for each epoch. So you can actually take a look at these. So the prediction here is a horse, but the label is a deer. So this is actually like a pretty blurry image. So like, I don't think I would actually be able to identify this correctly. So I guess our model is not doing such a terrible job. But as you can see, like for the plane, the model predicts correctly. But then for this cat here, the model thinks it's a dog. So it's definitely something interesting to pick up on. Let's see, do you have any questions or debug? What's device? Okay, so device is just defined like way at the beginning here. So the second cell here checks if a GPU is available. So if it is, then the device would be a GPU. And if not, then the device is just going to be the CPU. So for me, I have selected my hardware accelerator to be a GPU. So that's why my device here would actually be a GPU.
So we have one more question. Why does it need to know the server/computer? Does that affect it? Yes. So we didn't include this line of code because we were just assuming that you're on the CPU. But during training, we can actually put our data onto the GPU itself and using that device parameter. So that'll help us speed up the training and stuff like that. So we'll share the line of code later on. Jenson, actually, you could maybe just type that line of code in. Just port it to the device.
Wait, which line?
Oh, yeah, to device. So in the training loop.
Oh, to device.
Mm-hmm.
Oh, okay. Yeah, so we're basically just, I guess like, wait, let me think. Okay. So this actually doesn't, I think this, you have to actually make the conversion because like the tensor for a GPU is different from the tensor for when you're running on a CPU. So that's why I have to make this conversion here. But this is just like to convert a CPU tensor to a GPU tensor if you're using a GPU. So this is to avoid a specific bug.
Yeah.
That we have discovered.
Yeah, exactly. We just need to put it on the. So to device means put it on the GPU and do everything from there. So yeah, GPUs, for those of you who don't know, are actually very good for machine learning, for deep learning, because they are very fast with matrix multiplications, which is the entirety of deep learning. So that usually helps us. But again, don't worry about the hardware internals. We have another question. I'm getting an error about forward. Forward takes 0 positional arguments, true or given. I'm guessing the error is probably in your implementation of forward. You probably didn't specify that there were input parameters in your definition.
Yeah, so let's take a look at the CNN class here. So the forward function takes in, the first parameter is just self, which is, I guess, just a convention for Python. And then for the second parameter is x, which is your input. So I guess in this case, this would actually be your batch input. So yeah, make sure you specify those two arguments.
Okay. Any other bugs? Any other problems? Does anyone like see these kind of images like popping up, accuracy? So obviously the very important thing to see is that your accuracy keeps going up, or at least to an extent.
Yes, I only ran for 10 epochs, so I guess the model should not overfit just yet, but if your accuracy go down, then it might be a sign of overfitting. So it's actually gonna be, so I'll leave this as a challenge for you guys, but if your model is starting to overfit, then try to come up with ways to, I guess, alleviate that. How many samples were in each epoch? So you mean training samples or testing samples?
I think they were both 16, so.
No, but for each epoch though. It's just, I think it's just all the data set in your train loader and test loader.
Right, you're right. The visualization is just simply something that we wrote to kind of show you what the images are. It is more than 4 images, of course. I think it's like 60,000 images. So
yeah.
So yeah.
So train has 50,000 and test has 10,000.
Yeah. Okay, wait. Somebody else had an error. Matrix dimension 1 must match matrix dimension.
Yeah. So this
0. Okay. Yeah.
So if something is implemented incorrectly earlier, this is where it would show up. So
yeah.
I guess. Okay, is the breakout room open?
I can open that up. Let's see.
Okay, test function.
Let participants choose a room. Questions. Yeah. So if anyone wants to share screen and ask us to debug, help you debug, this DM one of us and we'll hop into the breakout room with you. But again, yeah, keep asking questions in the chat as well. That's completely fine if that's what you prefer. Open all rooms. Great. Yeah, if you have a doubt, let us know.
So I guess the accuracy that I got is 64%, which is pretty decent. So I guess at the end of training, it still thinks this plane here is a bird, but I guess I don't really blame the model because I don't think I would have been able to, I guess, classify that correctly myself. Okay, hopefully everyone is doing okay. So I guess if you have any issues with your with training and evaluating your model, then feel free to hop into one of our breakout rooms. But I guess the last thing here is just saving the weights. Just because we don't want to like necessarily retrain our model every time we, I guess, start our new runtime. So this is actually something that I think we did for our PyTorch workshop. So if anyone has an answer, feel free to type it in chat. Could someone help me out? My loss is constant over epochs. Okay. So there's no exceptions, right?
No, it's running just fine. It's for whatever reason not updating so the loss is being constant or something. So the accuracy isn't improving at all.
So the loss is constant, the accuracy is also constant?
Yeah, it's stuck at 10%. I figured it's not
mine's
updating
doing
my
that
model.
too.
Okay, so I guess, do you guys like type out loss dot backward? Because if you forget that, then it would remain constant.
I have it.
Yeah, I did too.
It's actually a little bit hard to debug without looking at your code, but since I'm sharing screen now,
what accuracy are you guys getting right now?
10%.
10%.
10%.
Yeah.
Oh, so you're classifying it randomly.
But the model should still, I mean, I would assume that it would adjust the weights and somehow affect the accuracy at least by like 0.1%, so I can see the difference, right?
Yeah. Yeah, actually, if you can hop into one of the breakout rooms, I think Sudhanshu should be able to help you out more.
Okay, I'll do that. Thank you.
Yeah. Feel free to stick around after the workshop is over as well, and we can deal with issues you guys have then as well.
Yeah.
Just wondering, are you gonna go over the like saving the weight section too?
Yes.
Okay.
I guess I'll give everyone like maybe like 5 minutes to debug.
Yeah.
Is anyone going coming across any other errors, or is everyone like good? You guys can like respond like thumbs up or anything that works.
All right, I think everyone here should be good, hopefully.
Yeah, so most of the people are in the breakout room right now. But honestly, like, I don't know, saving the weights and loading the weights are like very simple. So
Yeah, it's something that we did in I think our PyTorch workshop. So I'll just delete these cells. Is it torch dot save model state dict and then path? Yep,
pretty much. You got it.
exactly. So let's see. First parameter is the model dot state dict. And then for the path, I guess I'll just use model dot point parameters. So it's saved in this file here. So all the files in Colab is going to be recycled once your one runtime gets disconnected. So what you can do is you can actually download it onto your computer. Actually, I'm kind of curious what this will look like, but
I think it's a PyTorch file. I don't know if you guys have like the necessary application to open it, but yeah.
I think you can just open a text editor.
That's fair. Actually, can you open it? I want to like see how it looks, if you can open it.
I think I'm only sharing screen on Chrome though.
Oh, gotcha. Yeah, no problem.
Yeah, I guess I'll have to redo the screen sharing. Okay, let me try to open this. Are you guys looking at my screen now? Or Colab notebook?
We can still see it's your Colab notebook, yeah.
Okay.
Oh boy, the bugs must be serious. They've been in there for a while.
Yeah, usually like, I guess TensorFlow 1 is even worse, but yeah, basically
dude, it's terrible.
Basically with PyTorch, like, or any deep learning model, if you made like a small mistake somewhere, then it'll all come up at the end. So that's why it's important to, I guess, learn how to read the documentations.
So like if we wanted to try to like take steps to increase the accuracy in the future, what are some things we can do besides like, do we just like play with the hyperparameters, or is there something we can add to it?
So first thing first, you should increase the number of epochs, because I only did 10, because I think it'll take forever if I do something like 50 or even 100. But in principle, if you do like more epochs, you'll get a better accuracy until it starts overfitting. In which case, there are like multiple things that you can do to stop or slow down overfitting. And then another thing, like you suggest, would be to play around with the hyperparameters. So one of the hyperparameters would actually be the learning rates. So you can specify it in your optimizer. So the default value for learning rate is 0.001. So you can definitely play around with the learning rate. let's say we do like maybe 0.002 and see what happens.
Honestly, even kind of replicating some of the architectures of like well-known and successful models could also potentially like give your accuracy a pretty decent boost. So yeah. Just research on like different architectures available out there.
I think there's an article called Illustrated 10 CNN Architectures. So I guess the model that I implemented is kind of basic. So it's like based on LUTNets 5 from 1998.
1998. Oh, wow.
Except I changed some of the average pooling to max pooling and TANH here to ReLU.
So do those models just differ in their like amount of like max pools and convolutionals and things like that? Or is there like something deeper that they change?
So yeah, so I think a lot of newer models of high accuracy actually is a lot deeper, as you can see.
Mm-hmm.
So
what are those little R's next to it?
R is just the activation function. So R stands for ReLU.
Got it.
T here stands for TANH. And S is just softmax.
Got it.
And then another thing here is you see these brackets here. This like basically indicates like whether a layer is like repeated or not. So AlexNet is a lot deeper than LUTNets 5. So that's why its accuracy is also like a lot better. And it also has a lot more parameters. And then if you look at some like newer architectures like VGG 16, like there are basically like so many ways that you can like combine like different layers in a CNN. So yeah, as you can see, there are like 138 million parameters. So this would not be feasible on Colab. You would definitely need a better GPU for that. So one way to increase
models
the
that
Sorry, go ahead.
I was gonna ask, are there any models that like adjust their own hyperparameters as they go to like try to create that accuracy, or is that something that like is too hard to actually find out how it's affecting the model itself?
So I think one thing you can do is cross-validation, but like there usually like the hyperparameters that you would tune would be like the learning rate, the batch size. But if you want to actually like change the architecture of the model, like if you want to change the kernel size in all your convolutional layers, that would take a while. But as in principle, you can do it in the same way that you would like tune your learning rate or batch size.
Got it.
But I don't think we actually went over cross-validation in our workshop, so. Okay, so increasing the learning rate actually doesn't improve the accuracy. So that's something new. Okay, I guess the last thing would be trying to, I guess, reload our model from our weights.
Yeah, also quickly, just to mention, I tried opening model.pt and it is absolute gibberish. So like even in a text editor. So I don't know if there's like an application that will let you open it, but usually you wouldn't have to like open it for any reason other than to like obviously load in your weights and stuff. So yeah.
Okay, I guess it's just a binary file then.
Yeah, essentially.
Guess you learn something new every day.
Mm-hmm. Yep.
Okay, so power outage, you have lost all your weights or have you? So let's try to create a new instance of our CNN class and reload the weights. Does anyone have an answer for this? Model.load state dict torch.load path. Yep. Exactly.
Can you just use the same model parameter from before? Or do you have to define this new model at the top?
Okay, so I guess we're assuming like we no longer have our old model here, so
Oh, okay.
we only
Yeah.
have this file called
Ye-
model.pt. So we're trying to create a new model that's based on our old model.
Yeah, so the way this would like work in reality, like in production, for example, you would train your model like locally on your computer or whatever, and then when you want to like push maybe like a website or an application into production, you might end up like uploading like your .pd file on a server, and then you might have like some script on the server that like loads in the model and like initializes a new CNN or whatever, and then accepts like requests from the application. But essentially you would like want to like export your weights and like import them into a newly initialized model when you like push like whatever you want to use your model into production, or if you just kind of like want to share your weights with other people.
Got it. But in this case, if we're like going off the assumption that we've lost everything, then how does the new model take on the characteristics of your old one? Because wasn't CNN, like, aren't we assuming that we lost our CNN definition?
No, actually, what I mean is we still have the code. We still have everything we wrote.
Oh, okay.
But then our model's no longer trained because our runtime has ended.
Got it.
Or our
Okay.
power went out or whatever. But yeah, I guess if you somehow lost your Jupyter notebook, then yeah, you basically have to start from scratch. That would be
Got it.
kind of unfortunate.
Yeah, I mean, well, you've done like most of the heavy lifting at that point, because essentially your CNN. So in this, I believe when you export your weights and stuff, and I'm not sure if this is like accurate, so correct me on this, Jenson, but I don't know if it like also exports like information about like all the layers and stuff you had. You might have to like end up redefining them. So, but yeah, that's a lot easier to just redefine your layers than to like train your entire model all over again with and like getting the weights again. So
so training
pretty much
takes a long time, as you can see from me just running this cell. So if you want to train over like 200 epochs, for example, you might have to wait for literally like hours. So you definitely don't want to lose all the weights after like spending all those time like waiting.
Got it.
So yeah, if everything is correct, you should get all keys matched successfully. And yeah, that's basically the end of our guided projects. I think a lot of people are still debugging.
Thank you guys so much, by the way, for all this.
Yeah, no problem.
Yeah, no problem. Happy to do this.
I just came from the breakout room. What like accuracies are we getting for this model?
So
I think we
after
get
like
around
10
60%.
epochs, yeah. After 10 epochs, we get about 60%.
Okay. And is the loss supposed to like not strictly decrease?
Okay, so that's a good
It should
question.
probably level out after a while, but yeah, just reconfirm.
So basically the loss here is actually the loss of our final batch. So that's why there's some variation. If you want the loss for your entire training set or training data set, then you can actually do something like losses. You can create a list where you store all the losses.
Oh, okay.
So there's like I think there's a bug from the guided projects from the last quarter, but then we never actually confirm if it's a bug or not. I'm assuming it's a bug. So basically the loss is just a list with all your loss here. And then in order to get the epoch loss, you would have to do something slightly more complicated. So you have to sum up all the values in the list and then divide by the number of samples that you have.
Okay.
So
the one that's being printed is the loss for just one batch. So
yes, the loss for a final batch.
Okay.
So that's why there's some variation. But in general, the loss should still decrease, but it might be a little bit volatile. Change this back to default.
Could you go back up to where you sum the losses? It's just sum dot losses for the. Yeah. Okay. Wait.
Yeah, I guess don't worry about a specific like code because I'm gonna upload this notebook like I guess soon after the workshop. So if there's still some like bugs that persist, then feel free to compare your notebook to my notebook. Let's see. So loss here, I believe, should strictly decrease at this point. So far it has gone from about 0.1 to 0.08 to 0.07. And then now it's 0.066. .061. Okay, so that should be, yeah. I guess I'll just copy it and paste this in chat in case any of you guys are wondering. So yeah, if you have any lingering questions, feel free to ask them in chat. Okay, so I got a slightly better training accuracy of almost 64%. So hopefully you should get something similar.
So for models like this, I guess in industry 2, do we really only care about the highest one that we can get? Because then we can just transfer over those weights.
Oh, you mean the highest accuracy?
Yeah, just at all your training ones.
I guess for this particular application, then I think the highest like accuracy should come near the end until you start to overfit. So one way to stop that is to if your test accuracy starts decreasing, then just like stop the training. So that's, I believe, what is called early stopping.
Okay.
So that's one way you could improve this train test loop here.
Is there ever a situation where you'd care about like the consistency of a model compared to just like the highest one run that it can give?
Wait, what do you mean by consistency? Like,
So like in the end we can like after running all these training ones,
Mhm.
in the end, oh okay, since this one is cumulative, in the end we can only take the final weights and biases, right? Like when we're transferring
yes,
it. Okay.
but
So
I guess what you're asking is if you can like stop the training earlier, if your accuracy is for some reason decreasing.
yeah, or if there's like a way to run a bunch of epochs even if you overfit, but then find the weights and biases that gave you the highest accuracy of all your epochs and just use that one. Is that
I
a
actually
thing or
see
no?
what you. I think you can. So the way you get your model parameters would be just do models dot parameters. You can actually save this into a variable, I guess, and then you can. Actually, I'm not sure if there's a way to. I think there should be a way to actually initialize a new CNN model with your model dot parameters that you save. Actually, don't remember off the top of my head, so let me look this up. Uh, or I guess another way would actually be just like, I guess doing the saving your state dictionary into like a file for every epoch. Oh, that would be a little bit wasteful, I guess. So you can do something like this.
Oh, okay. And then eventually you find which model had you could also do one where you find the highest one and just load that one in constantly if it's just higher than the last, right?
Uh, Actually, do you mean like doing that in your loop? Because like I don't think
Or
you should like change the state of your model like in the middle of your training.
yeah. I
I
meant
don't think that's
I see. Okay. Yeah, but that makes total sense. And then you can just grab the ones that produce the highest one.
yeah. So this is kind of like a brute force approach. I think there should be like. Let me see if there's a smarter way to do this. Okay, so I believe this is actually a recommended approach. Okay, so as you can see, there are like a lot of files that are being saved as the training is progressing. But I guess if you want to be a little bit smarter, you can do like, although I wouldn't be able to strictly tell what the accuracy is. So, okay, I'm gonna write some pseudo code here. Let's see. Last epoch is greater than accuracy. And yeah, so you only do this, you can add some logic. Like if the accuracy from your last epoch is greater than this epoch, then you can save it. So this would ensure like you wouldn't just like, I guess, waste too much space on your computer just by saving all these weights.
Yeah.
But yeah, in order to figure this out, you would want the test to actually return something. So you can just return, I believe, this number here. This should be your accuracy. And then you would just store it in the variable.
Hey Jenson, how's it going over here? Is everyone good?
Yeah, I think we're basically done at this point.
Okay. Well, we're helping some people debug right now. So question to everyone, did you ever experience an error where the accuracy didn't change like over the epochs? Did anyone experience that or try to fix that? Oh, you had that. Okay, so do you know what the problem was? Yeah, we have a couple people in the breakout room who are trying to figure that out right now, and I
Oh,
think
you guys are still trying to figure it out. Okay.
Oh, so the learning rate was too high and I was overshooting. So the symptom was that, I mean, the accuracy didn't change at all, or was it like decreasing? Because for them, it's like, it's just not changing.
I think someone said their accuracy is always at 10%.
Oh, yeah, exactly. Wait.
Oh, yeah.
Which I think
Yeah.
they're just classifying it randomly at that point.
Oh, so you're saying that it was just too high? Okay, so what did you set it to in the end? Well, I think we have
Okay,
0.001.
so that I don't think that's like overshooting. So I just use the default value here, which is 0.001.
Okay, that's.
If your learning rate is too high, it should actually diverge. So you should see your loss like blowing up to infinity.
But maybe that's what's producing the 10%, because isn't like an insane loss like that gonna lead to just like random guessing in the end?
So you have 1 in 10 chance, right? So wait, so did you fix that as well by changing the learning rate, Jacob?
Oh no, I didn't have that problem.
Oh, you didn't have a problem. Okay.
But I guess if your learning rate or if your loss is blowing up, then it should be pretty easy to notice.
Yeah. So is the loss staying
But
the
I'm
same
guessing
too?
that's not the issue.
Yeah, wait, Eric, do you see your loss ballooning as well, or was that like kind of stable? Or like increasing slowly or whatever? The loss stayed the same. Okay. Yeah, that's what they're having as well. Okay. Let me drop back into that room. Seems to be a common issue. I wonder if the learning rate is just too high. Questions?
Can you go over again how you determine the dimensions for the flattening thing? Because I tried to add like another convolutional layer between the first and the second, and it threw my dimensions off somehow, and I'm not sure.
Yeah,
why.
so if you add more layers, then it's pretty normal that you have to like figure out the dimensions again. So I guess actually a good way to do this is to do the math, because I think that's a very useful exercise here. So the input, okay, so do you remember what the input size is? Or input dimensions?
The input, like of the image?
Yeah, or the batch.
Isn't, I think the image was like 28 by 28. I don't remember.
Wasn't it 32 by 32? Or am I thinking of something
Yes.
else?
It's 32 by
Okay, sure.
32, and then there are 3 color channels. So I'm gonna add a 3 at the beginning. Okay, so what is the output of the, or the dimension of the output of the first convolutional layer?
It's gonna be the same, but with 6 output channels instead of
Yep, exactly.
3.
So what's gonna happen after our first pooling layer?
Right, so it's gonna reduce it or divide both dimensions by 4, or by 2.
Yep. So it's 16 by 16.
4.
And then,
Okay.
okay, let's work this through. So what was the output dimension after a second convolutional layer?
Is it
Same thing.
16 by 16 by 16?
Yep. And what's the output dimension after the second pooling layer?
16 by 8 by 8?
Yep. Okay, so after we do flattening, I can actually replace this by, or 1024 by 16 by 16, or 16 times 8 times 8. So that's, if you do the math, it's exactly the same. So this is how you would, I guess, debug your model if you run into a bug.
So if we add in another layer there, like in between.
So like after,
yeah, after the second pool.
okay,
Would we just choose an arbitrary amount for the next number? Like instead of 616, it'd be like 16 and then 25 or something. Like how do we decide that? Just guess or check.
so in channels has to be 16, as you said. The out channel is a design choice, so you could do something like 25, and then kernel size is also a hyperparameter. So I guess you can do 3 or 5. And then the default stride is 1, but I guess you can change it up. And also the padding here should be, it actually depend on your kernel size if you want to do same convolutions. So doing same convolution just makes the math a lot easier, as you can probably tell. Because if you don't have the padding here, the output dimension of your convolutional layer is going to be different. So yeah, I guess so actually if you want to, like, if you don't have any ideas what your kernel size or what your, actually this doesn't really show how many feature maps there or how many filters there are, so.
Yeah, I
just
just want to give a quick update. So we had a problem in the other breakout room, which got resolved. We're not exactly sure how. Probably some kind of leftover state or some kind of weird bug, but the 10% accuracy is done. So I think, how is everything going here? Everyone seems to be in good shape to train that previous model, though.
Yeah.
Yeah, is everyone like good to, like,
Yeah,
everyone
actually,
has like a model running and training?
Actually,
If anyone isn't,
you should probably do the concluding remarks first, and then we can debug if there's any lingering bugs.
Yeah, absolutely. Let me actually just share my screen then. 2021 current project. All right. So hopefully, so you all got a taste of what it's like to kind of implement a model. And as you can see, there's a lot of bugs. It's a huge piece of code, like hundreds of lines, not maybe not hundreds of lines of code, but a good chunk of code. And it's not that easy. But what's really important is always look at the documentation. And hopefully you all have something that's up and running. If not, please feel free to stay back. But this is pretty much the end of advanced track. And we wanted to kind of quickly summarize everything that we've covered this quarter, so everyone has a high-level view of the topics you're now pretty comfortable with. So we started off with feed-forward neural networks. We did the theory. We've also implemented that in the PyTorch workshop. Then we covered the theory of backpropagation. Then we did CNNs, which I'm sure you all are very, very familiar with after this workshop. Then we did RNNs and LSTMs along with ResNets. Then we covered Anaconda and PyTorch. Again, we hope you all are very comfortable with PyTorch now, or at least getting more comfortable. Remember, documentation is always everything. And congrats on making it to the end. Like, we really appreciate you all sticking it through the quarter. So what comes next is, I think, the most important thing: explore stuff on your own. Medium is amazing. People, I'd say, Medium is like a huge, has really helped deep learning advance because there's so many great articles. Please check out some of the articles on Medium. And some additional topics. This is a non-exhaustive list. So look at regularization, batch normalization, ADAM, transformers, GANs, reinforcement learning, autoencoders, unsupervised learning. And there's a lot of really, really great topics. Deep learning is like kind of taken off only in the last few years, I'd say. And it's only become so powerful and so accessible in the last few years. So please explore all of these. There's some great resources for all of this stuff. And ACM AI also puts on the Advanced Plus Plus workshop series, where we cover stuff like ADAM, transformers, GANs as well, autoencoders as well. So even regularization. A lot of these topics actually covered in Advanced Plus Plus, so definitely check that out. And of course, sign up for the projects team. Because as Edmund and Frank have both said, it's a really, really fantastic way to apply all the stuff you just learned. And it's a really cool problem, classifying whales, making sure you identify them. And you'll see a lot of the stuff we use here, a lot of the code components can be reused in your own model. That's the kind of stuff we've made. Is like very, very general and really, really powerful stuff. Okay. So thank you all so much for a really great quarter and for attending all the workshops. We really, really appreciate it. If you can drop the link in the feedback form. And yeah, that's the end of advanced track. Thank you all so much for coming.
Thank you guys so much.
Yeah, you're welcome.
Ooh, it's good stuff. Good stuff.
Thank you.
You're welcome.
Yep.
I'm going to end the recording. And thank you
Yes,
also
same.
everyone who